Hi there, in this lesson we're going to be looking at exponential decay and really modeling exponential decay. And we've talked about exponential decay a little bit before. We already kind of have the definition for it in our notes. We know when to recognize it in terms of the equation. But basically exponential decay is an exponential function in which y is decreasing as x increases. In other words, as we go from left to right, the function is going down, is decreasing. And so when we look at these things, the reason it's decreasing is because, remember when we looked at this before, that's when the b value was between 0 and 1. And so we have two forms of this thing, and these are going to be very similar to exponential growth. The first form is our standard model, and just like growth, this is used when we have these things increasing at specified time intervals, okay? So like an account or something that was growing every month in terms of growth with our standard, where it wasn't growing all the time, it was growing at the end of each month. It's the same thing here. Something like depreciation, where something that we have purchased is losing value, is depreciating it. Well, it's not constantly losing value in terms of the way we look at it. Maybe at the end of the year it loses a certain amount of its value, and at the end of the next year it loses a certain amount more of its value, okay? That's the standard model when we're on a specified time interval. A lot of financial examples and things like that are going to fall into this category. And you'll notice it's y equals a times 1 minus r raised to the t. It looks almost exactly the same as growth, except for one minor difference, this subtraction sign instead of an addition sign. Okay, which makes sense because instead of increasing, instead of adding the percentage each time, we're going to subtract that percentage each time. The value is going to decrease at each unit. Okay, everything is still represented the same way as it was with growth. A is the initial amount, R is the decay rate, and T is the time. All right. So again, very similar to growth. We're going to use it the same way, except now we're decreasing instead of increasing. That's why we're subtracting the rate. All right. If we look at the continuous model, not a big surprise here either. The continuous model looks almost exactly the same as well, with one minor difference, this little tiny minus sign right here. Okay, we change it to a negative k to indicate that decay rate is bringing us down. It's decreasing the values. Other than that, everything is the same here. It's a of t, which again is function notation. This is just like saying y equals, okay? So this is the same thing as saying y equals a times e to the negative kt. And if you want to think of it that way so you don't get confused, that's fine, all right? But a of t is just a single variable. It's like function notation, just like f of x, all right? When I look at this thing, a is still the initial amount. K is now the decay rate constant, and t is the time. And notice the decay rate constant is still expressed as a positive. The equation's automatically going to make it negative. Like if I say I'm losing a certain amount of value here, I wouldn't say that my decay rate is a negative something. I would just say I'm losing this much. I'm losing 2%, or I'm losing 5%. Okay, so I still talk about it. We still think about it in terms of a positive, but then the equation makes it negative for us. All right, it makes us subtract that rate. All right, but we can just leave it in terms of the positive. And really, if you forget to make that negative, it's going to be pretty obvious when you get your answer. Your answer is going to be negative instead of positive. Just go back and change it and fix the sign. Okay, so it's a very easy fix, common mistake, but easy to catch, easy to fix. Okay, for example, if I look at something like this guy and something like this, a brand new car costs $32,000 and depreciates 22% per year. What will the car cost in 4 years? And when we talk about depreciation, that means that the car is losing value. When you buy a new car, it loses value, unless it's a collector's type of car, unless it's some kind of classic car. But it's going to lose value. It's not going to be worth as much. That's why used cars are cheaper. So what happens here is we reevaluate this each year, which means I'm going to use my standard model, the y equals a times 1 minus r raised to the t. That's an ugly looking 1 minus r. Let me try that again. 1 minus r raised to the t. And now from here, I just plug away. I start plugging in what I know. I know the initial amount is 32,000. Minus r, the rate is 0.22. Again, percentages are always expressed as decimals because a percent symbol really means out of 100, which means divide by 100. And now the time, again, make sure the units match here. That was the big thing with exponential growth. The depreciation rate is per year. The time is in years. The units match. I plug the 4 in. And now I just plug it into my calculator. And when I do that, it gives me approximately $11,844 And we'll round to 2 decimal places because it's money, and 82 cents. Okay, so that's how much the car is worth in 4 years, and that's pretty accurate. That's pretty legitimate. A lot of cars depreciate between 20 and 25%, depending on the make and model. Now, there are other factors that come into account here, like mileage and things like that, but the most prevalent when we're calculating this is how old the car is. Okay, so now the question is, the second question, the follow-up question here is, when will the price drop to $2,000? So this time, again, I'm using the same equation. The initial amount was still $32,000. The depreciation rate hasn't changed, but now it's asking how long. It's asking for me to use t as my variable, and I want to know when this thing is going to equal 2,000. So now I'm going to solve, and really, we've had a lot of practice with this. We're going to solve this the exact same way that we solved exponential growth. I divide each side by the 32,000. And again, I could leave this fraction the way it is if I want, but it's easy enough to cancel out the zeros and write this as a 2 over 32, which is 1/16. Again, if you don't simplify that, if you don't reduce it, it doesn't matter because we're going to be plugging into the calculator. Same thing here. It's nice to simplify this and write it as just a 0.78. But now from here, if I want to get that variable unstuck, I have to take the natural log of each side. So I'm following the same process I did before. The natural log allows me to bring that exponent out front. So I have t times the natural log of 0.78, and now I divide by that logarithm. And once again, this becomes a job for my calculator, so I'm just going to plug this in. And it gives me t is approximately 11.16, and that's in years. My percent was per year, my time comes out in years. And that's it. If I look at the next one, this is very similar to what we do with things like carbon dating, but we'll talk about a radioactive isotope has a half-life of 17 years. In 1983, there are 12 grams of the isotope present. How many grams of the isotope remain in 2015? So as the radioactivity releases from this thing, it changes the isotope, so it converts from one kind of element to another. Really, it's the same element, but a different isotope of that element. But anyway, when we do this, the first thing we need to do, especially when we're dealing with something like this, is there's a lot of information going on here. If I try to solve this right away, the thing I'm going to find I'm missing is the k value. So what I need to first do is find the k value. And this is continuous. It's not like it's waiting to release radioactivity. It's always doing it. So I'm going to use my continuous model. And don't forget that little negative sign there. If you do, it's not a big deal. Your answer is just going to come out as negative instead of positive. All right? So I plug in what I know. I know the initial amount was 1,200 grams. I know the k value is the thing I kind of want to find right now. So what I need is I need a time and a final amount that I can plug in. And half-life essentially is the amount of time that it takes to cut the initial amount in half. All right? So if I use that 17 in terms of years here, if I use that as the time, that's the amount of time it takes to cut the initial amount in half. So if I started with 1,200, it means I'm going to end with 600 over here. Okay, that's how half-life works, and this half-life is going to allow me to find the k value, and that's typical of these examples. So now what I'm going to do is I'm going to divide each side by the 1,200. When I do over here, that gives me a 1/2, which is not surprising because I'm doing half-life. This is going to give me a negative 17k for my exponent. And now from here, I solve it the same way I've always solved it. I take the natural log of each side. Over here, the natural log and e cancel out. So that leaves me with a natural log of 1/2 equals a negative 17k. And now I divide each side by the negative 17. And once again, this just becomes a job for my calculator. So when I do that, I find out that k equals, it's going to give me a 0.040, and I'll round it to 4 decimal places, and just say 0.0408. Okay, and keep in mind, if you forget that little negative sign in front of the k to start with, your k value is going to come out as the same answer but negative. Just be aware of that and change it back to a positive, or plug it in as a negative in the next part of this problem. Okay, but I'm not finished the problem. The problem asked how much of the isotope is going to be left in 2015. So I need to use that k value that I just found. The initial amount is still the 1,200. e to the negative 0.0408. And now from here, I got to plug in the time. So really, I'm going to be solving for the amount here. So I just need to know how much time has passed. Well, from 1983 to 2015, really, I'm just asking how many years is that? It's 32 years. Okay, so what I'm doing is I'm plugging a 32 in here. Same thing here. So I plug the 32 in. And now, once again, I plug it into my calculator. So this tells me that there are approximately 325.21 grams left. Okay? Everything else has been converted to something that's not radioactive. Okay? If we continue this example, let's say that after exposure to the breakdown of 1,100 grams of the radioactive isotope, a virus has mutated into a strand that initiates the outbreak of a zombie apocalypse. I can't believe it. In what year will this occur? So really, we're using the same information that we had up here. We still have the initial amount of 1,200, I believe it was. Yes, it was. So we still have the initial amount of 1,200. I still have the same K value, the negative 0.0408. And essentially, time is now the thing I'm trying to solve for. So I'm trying to solve for T. And I want to know when this thing is going to equal what? So if I have been exposed to 1,100 grams, that means 1,100 grams of it is broken down, which means there's only 100 grams left. Okay, so just be aware of that. I started with 1,200 grams. I take away what's been broken down, and that gives me 100 grams left over. Now I want to solve this thing. Okay, and I solve the same way I've always solved. I divide each side by the 1,200. Over here, that reduces very easily, so I'll just go ahead and reduce it to a 1/12 equals e to the negative 0.0408t. Now I take the natural log of each side, so I'm solving using these logarithms. Over here, the natural log and e cancel each other out. So I'm left with the natural log of 1/12 equals a negative 0.0408t. And now I divide each side by the negative 0.0408. And once again, if you forget that negative, your time is just going to come out as negative, which is obviously ridiculous. You can't have a negative time. You just have to change it back to positive. So now I plug this into my calculator. So this tells me that time equals approximately 60.9. And again, the units here are important because that decay rate was per year. My time is now in years. All right, so it's important to list that it's years that are being used here, okay? It all comes back to those units. So in about 60 years, things are going to go terribly awry. All right, so again, we're just solving this thing the same way we did exponential growth. We set up the initial equation. The difference is we have subtraction signs thrown in there in front of our rates, but then we solve the same way. We plug in the information we know, we identify the unknown, and then we either plug it into our calculators or we solve using logarithms. Okay? And the last thing is, I don't know why I even circled this thing. I just realized the question didn't ask how long. It asked in what year. So if it takes 60.9 years, remember we started in 1983, and we have to add that 0.9 years. So we'll say 61 years. So we'll say this is going to happen in approximately the year 2044. Okay? So just be aware of that. I almost didn't answer the question there, but that's the year. Okay?